Hi, my name is Johnson Son from StarFive Technology. Today, I'm presenting our first volume production high-performance RISC-V SOC. It is a small silicon from StarFive, but one gigantic step for RISC-V. I am proudly presenting our first volume production high-performance RISC-V SOC. It provides complete platform solution targeting mid-range and edge computing. Let's look at its key features. Technology-wise, it is on TSMC 28 nanometer. It supports operating systems, including Fedora, SUSE, OpenHarmony, Real-Time OS. Its RISC-V CPU subsystem includes 4 cores of 64-bit U74 running at 1.5 GHz with 2 MB L2 cache. Memory bandwidth supports DDR4, LPDDR4, and 2800 megabits per second. Of course, it also supports DDR3 and LPDDR3. On the right-hand side is our video input subsystems. We support MIPI, CSI, and then we also have our own ISP IPs. Video output, we support dual video outputs, HDMI, 2K at 60 frames per second, and then MIPI, RGB. In addition, we support very flexible high-speed I/Os, such as USB 2.0, 3.0, PCIe, eMMC, and then gigabit. This page shows the architecture highlights in 3 areas: performance, power, and security. As I mentioned we support 4 cores of running at 1.5 GHz with 2 MB L2 cache. In addition, we support trace and debug, which is very first in RISC-V systems. We also support hardware I/O cache coherency. We put a lot of efforts in low power design. It includes 8 power islands. It supports voltage and frequency scaling. As security goes more and more important, we also have our own security engines inside. We support security boot, program signature, tamper, leak, and crack proof. Let's look at this SOC's block diagram and the CPU subsystem. In our SOC, we have 10 major subsystems. On the top left is our CPU subsystem. Top right is our video codec subsystem, including encode, decode, JPEGs. And then in the middle left is our audio subsystem. And next to it, we have a miscellaneous subsystems, including many IPs, such as PMU, power management, DMAs, etc. And in the bottom is our video in subsystem with MIPI, CSIs, ISPs. And then moving to the middle right, we have our SRAM, boot RAM, and memory interface. And then 3G GPU video output, display controller, and HDMI, BP displays. In the bottom is our hardware security accelerator. To the right-hand side, we have two more subsystems. One is the high-speed I/O, PCIe, Ethernet, USB, and eMMC. And then in the bottom is our, of course, the DFX, JTAGs, PLLs, and thermal sensor. So these are our block diagram with our major subsystems, 10 of them. Now this page shows all the related components to support video processing. As I already explained it, we have the video in from the MIPI and ISP, and then we have on the top, we have video codecs, and then we have a 3D GPU to process it, and the video outputs. This can support a lot of multimedia applications. This is our audio subsystem. We have the audio DSP, which can provide a lot of different algorithms and enrich the quality of the audio. And then we have I2S, which can support, we have four channels of them, which can support audio systems up to 7.1. And we have SPDIF, audio DAC, PDM, DMIC to support many different type of applications require high quality audios. In terms of high-speed I/O, this has the AOP, DDR, and DDR4. So in terms of the high-speed I/Os, we have PCIe, Ethernet, USB, eMMC, which can provide really flexible interface for different designs, different products. For example, PCIe can expand to additional accelerators, or even add converted to SATA to many other different I/Os. With our very rich hardware support, without software, it won't work. So we pack of our SOC with a lot of softwares. We provide complete personal computing platform solutions. The softwares we have, including 3D GPU DDK, video streaming, display, audio processing, image processing. And they are fully open source to RISC-V communities. Let's look at the application. Our chip can enable products targeting cloud computing, industrial control, NAS, tablet, SPC, and also HMI, human-machine interface, which require a lot of graphics, displays, and interactions. Let's take an example of the tablet. This is a very typical systems in a tablet. Look at from the left, for example, a camera, data coming in, connect to the videos and pictures coming in, connect to our MIPI CSI through our own ISP and to the memory. And then CPU, GPU, and many other IPs can process the data and display it through our HDMI to the panels. So this is data path from the left to the right. IP camera, similarly, the videos or pictures coming in, and then go through our system and go through our USB or PCIe or Ethernet, go through the server or network. This can enable applications such as home security, civilian security systems. HMI market, so our chip can support interfaces and also a lot of processing, and then send it out to the panels through the MIPI, through our dual display controller and interface. So this is pretty much my presentation. And then if people wants to know when this product will be ready, so JH7110 will be released in Q1 2020. Thank you. If there's any questions, please send me an email, johnson.sun@starfivetech.com. Thank you very much.